Students, in the last tutorial we learnt on sets, and in the sets we discussed on the different types of sets, the properties of sets, union, intersection, and many more, and many problems related with sets. Now in this section you will find the relation concepts of relation. First of all, you learned on ordered pair. What is ordered pair? Okay, so two numbers a and b are listed in a specific order and closed in parentheses form an ordered pair. Like this, it is written a comma b and it is written in a parenthesis, and obviously you should remember that a comma b is not is equal to any way b comma a. Okay, so this is a one important concept, and you can take a point say a which is say 2 comma 3, another point say b which is your 3 comma 2. Now you observe carefully, if we plot these 2 points a and b in the Cartesian coordinate system, you will find that these 2 points are actually separated. So you can say that these 2 points are not actually same. So in other words, we say that a comma b is not any way equal to b comma a. Okay, now the Cartesian product of two sets. You know, a and b be two non-empty sets, and the Cartesian product of the sets a and b is the set denoted by a cross b. Okay, this is the notation for presenting a Cartesian product between two sets a and b. Obviously they are non-empty sets. Now consider that a ordered pair, this is a comma b, small a small b, such that the first element is small a comes from the set a and the second element b from the set b. Okay, now in this case, if we find that a cross b, that is a new set which is the Cartesian product, contains the elements like that a comma b, where the first element is written from the set a and second element is from b. So this type of elements will be retained in the Cartesian product of a and b. Okay, now if you consider a set say a comma b, and b is another set which is containing the elements 1 comma 2, and you have to find out the Cartesian product between these two sets a and b. So in this case, what will you do? It is actually given to you to try, but I am doing this one. Suppose you make a 2 by 2 box. Okay, in this box I write in this way, say this is set a and this is set b. Set a contains the elements small a and small b, and set b is containing the elements 1 comma 2. Now if you write all possible ordered pair, then you have to write first element from set a, second element from set b. So a comma 1 in this way, and this will be a comma 2, and this is b comma 1, and finally b comma 2. So there are 4 ordered pairs, respectively a1, a2, b1, b2, or you may write a cross b as like this. The elements are a comma 1, a comma 2, b comma 1, and b comma 2. So the cardinal number of the Cartesian product a cross b is equal to 4. Okay, next page. Now you find the definition of relations. Let a and b be two non-empty sets, then the relation R from a to b is a subset of the Cartesian product a cross b. This is very important. So if you consider a relation from a to b, this relation will be a subset of the Cartesian product a cross b. So in notation I can write R is a subset of the a cross b, Cartesian product a cross b. Don't try to understand capital R as the set of real numbers, because this is actually the relation from a to b, set a to set b. So this relation is a subset of the Cartesian product a cross b. Now as earlier you have taken set a is containing the elements say is small a and small b, and set b is containing the elements 1 comma 2. So what will be the elements of a cross b? Obviously, and there are 4 elements, a1, a2, next is b1, and finally b2. Okay, so these are the 4 elements. Now under some circumstances you can consider a relation say R which is a1 and say b1. This is the relation. Okay, 2 elements are taken in the relation are respectively a1 and b1. Obviously these are is a subset of the Cartesian product A into B, A cross B. Okay, so relation is nothing but the subset of A cross B, or the Cartesian product A cross B. Next page, domain, range and codomain of a relation. This is very important. So first of all, you have to understand what is domain. So you consider a relation R from A to B such that R is a subset of A cross B, and this set of all the first coordinates of the elements of R, that is the relation R, is called the domain of R, and in short it is written as DOM in bracket R. Okay, whatever you write in the full statement, domain of R or DOM in bracket R. So the set of all the second coordinates of elements of R is called the range of R. As for example, you can take an element of a relation R, say A comma B. So A will be the element of the domain and B will be the element of the range, and the total set B is called the codomain of the relation R. You have to see an example that will be better for understanding. What are the domain and range of the relation? The relation is taken as capital R, minus 1, 1, 1, 1, 2, 4, minus 2, 4, 3, 9. Minus 1, 1 is an element of the relation R. Okay, 1, 1 is also relation element of R. If I say 1, 1 is an element of the relation R, that means 1 is related with 1. Okay, 1 is related with 1. Now, as I earlier discussed, that the domain is nothing but the set which contains the first element of the relation. So here it is the domain will be minus 1 and 1, obviously another element minus 2, 2 and 3. You just observe the first elements. This is minus 1, plus 1, 2, minus 2 and 3. So we have written the domain as minus 1, 1, minus 2, 2 and 3. And what will be the range of the relation? Obviously the set which is containing the second elements. Okay, second elements will be the range set. So what are the elements? These are respectively 1, 1, 4, 4, 9, but you have to write only the single element. 1 cannot be repeated. 1, 4 and 9. These are the second elements, 1, 4, 9. Okay, so in this way you can find the domain and range of a relation. Now how to get the codomain of the function? So better you consider a set, say capital A, which is containing the elements minus 1, plus 1, minus 2, plus 2 and 3. Another set B which is containing the elements, say 1, 2, 3, 4, 9. So in this case, obviously you have got the domain as this one and the range as this one. So obviously what will be the codomain? The codomain will be the set B. The set B, that is the elements, the set which is containing the elements 1, 2, 3, 4 and 9. This is the codomain of the relation R. Okay, next page. We take a question. Say let A is equal to 1, 2, 3. This is a set, and B is another non-empty set 2, 4, 6. Show that the relation R 1, 2. This is relation is nothing but the element which is containing the elements in ordered form. Okay, 3, 4 is a relation from A to B. Find the domain, range and codomain. Codomain is obviously this last set, that is the set B. Okay, you consider the set A and set B, and set A is containing the elements 1, 2, 3. This is given in your question. B is the set which is containing the elements 2, 4, 6. So these are here. And in the example, you find that R is containing the elements 1, 2. That means 1, 2 is an element of the relation R. That means 1 is related to 2. 1 is related to 2. In this way, say 3, 4, last element 3, 4. 3, 4 is also belonging to the relation are that means 3 is related with 4 in any way. So if I draw the pictogram, you see that 1 is related with 2, 1 is related with 4, 3 is related with 2, and finally 3 is related with 4 in some way, in some circumstances. Okay, so what will be the domain? The domain is the first coordinate from the set A. These are nothing but your 1, 3. And what is the range? Range will be the second coordinates, that is 2 and 4. So in the range you will find 2, 4, and finally codomain will contain the total set B. That means your set 2, 4 and 6. Okay, this is the codomain set. Next is the properties of relation. Better you write everything whatever I am discussing here. This will help you in your board exam or any related competitive exams. Okay, what are the properties of relation? First of all, we discuss with the reflexive relation. A relation R on a set A is called a reflexive relation if A, A belongs to R. That is, A is related with A itself. For every element, A is belonging to the set A. Okay, so are the following relation on A, that is 1, 2, 3, 4 is reflexive, are reflexive. So first of all, you take the this is the set A, 1, 2, 3, 4, and the relations are given 1, 2, 3, 4, 3. 3 examples are given. So first of all, you observe the first example. Here 1, 1 is an element of R. So this is correct. 3 is related, 1 is related with 1, 3 is related with 3, 4 is related with 4, but you see that you have an element 2 in the set A, so 2 should be also related with 2. So you find that 2 is not related with any way 2, so this is not reflexive. Okay, this is not reflexive. This is not reflexive. The first one is not reflexive. Second one is related with 1. Okay, fine. 2 is related with 2. This is also correct. 3 is related with 3, and 4 is also related with 4. All the elements of A is related with itself, so this is a reflexive relation. Second example is reflexive. Okay, this is a reflexive relation. And the third one, you see that 1 is related with 1. Okay, fine. 2 is related with 2, that also fine. 3 is related with 3, but 4 is another element of the set A. Here we find that 4 is not related with 4. That means 4, 4 is not an element of the relation R. For this, this is not a reflexive relation. This is not a reflexive relation. Okay, very simple. Next is another properties. We take a set A which is non-empty, and A is said to be the symmetric relation. Okay, A is said to be symmetric relation if you find that A, B, and that is the ordered pair, belongs to R, also simultaneously implies that BA also belongs to R. Okay, provided A, B are the elements of the set A. Okay, in short, in notation you can write ARB implies BRA for all the elements A and B are the elements of A. Okay, and this will be anti-symmetric if you find that AB belongs to R and BA belongs to R. That means A is related with A is related with B, and B is also related with A, and if you find both combined implies that A is equal to B for all AB belong to A. In this case, the relation R will be anti-symmetric. Okay, next is your transitive relation. If you find that AB is an element of R and BC is also element of R, in this case AC also belonging to the R. That means suppose A is an element which is related with the element B, and B is an element which is related with the element C, and if you find that A is also related with C, in this case the total relation will be a transitive relation. Okay, so in short you say that ARB, BRC implies ARC for all ABC belonging to the set A. Okay, next we take a question. Are the following relations on A, that is 1, 2, 3, reflexive, symmetric and transitive? We have to check what is the relation. Okay, first relation is, this is the first relation, okay, 1, 1 or 1, 2, 2, 2, 3, 3, whether it is reflexive, check it. 1 is related with 1, okay, fine. 2 is related with 2, that also fine. 3 is related with 3, and that means this is reflexive, okay, reflexive. The relation is reflexive. Next, check for the symmetric relation. Here it is 1 is related with 2, okay, 1 is related with 2, that means 1, 2 is an element of the relation R, and 2, 2, that means 2 is related with 2, and in this case it implies that 1 is related with 2, is it? Yes, 1, 2 is an element of the set. 1, 2 is an element of the relation R. Okay, for this is a transitive relation. This is a transitive relation. This is transitive relation. Next, check for the symmetric relation, whether it is symmetric or not. You will see that 1 is related with 2, that means 1, 2 is an element of the relation R. Does it imply 2, 1 is also an element of the relation R? No way, there is no element, so this does not imply, okay. 1, 2 belongs to R, but it does not imply 2, 1 is an element of the relation R. So this is not actually symmetric. This is not a symmetric relation. This is not symmetric relation. Okay, final one, relation number 2, 1, 1, 2, 2, 1, 2, 2, 1. First of all, you said 1, 1 is an element of the relation R, 2, 2 is also relation of R, but you are not finding that 3, 3 is not an element of the relation R. For this is not reflexive, okay, this is not a reflexive. Next, you observe for the other relations. 1, 2, here it is 1, 2 is an element of the relation R, and it implies that 2 is also another element which is belonging to the relation R. 2, 1 is also belonging to the R. So this is symmetric, okay, this is symmetric relation. Finally, check for the transitivity. Yes, 1, 2 is an element of R, it is here, and 2, 1 is another element, 2, 1 belonging to the R. Whether 1, 1, that is first and third, is belonging to the relation R, 1, R, check for it. Yes, it is here. 1, 1 is also an element of the relation R. For this is transitive relation, okay, this is transitive relation. So when a relation is symmetric, reflexive and transitive, the relation is equivalent relation, but none of them is equivalent, because first one is reflexive, transitive but not symmetric, and the second example is not reflexive but symmetric and transitive. Okay, next is what is equivalence relation. Earlier I said a relation is said to be equivalent relation if it is simultaneously reflexive, symmetric and transitive. Okay, let's check. So that the relation is parallel to, on the set S of all straight lines is on a plane P is equivalence relation. Let's check. Let us consider that P be the plane, and in this plane there are straight lines, and S is a set which is containing the straight lines, say L1, L2, L3, L4, like this. Okay, this is a set of the straight lines. Now check for the symmetric. We consider a line, say this is the line L1, okay, this is the line L1. Obviously you can say that L1 is parallel to L1 itself. What is the relation given? The relation is given is parallel to, okay, is parallel to. So any line is parallel to itself, you can say that. So yeah, it is L1 is related with itself, okay, L1 is related with L1. That means this is a reflexive relation, a reflexive relation. Okay, this is reflexive relation. Obviously L1 is an element of the set S, okay, L1 is the element of set S. So the first property is proved. Second property is, you consider another line, say L2. Okay, L2 is another line, and this L1 is parallel to L2. Okay, does it imply that L2 is also parallel to L1? Obviously if a line is parallel to another one, so it will be vice versa, isn't it? So this is symmetric, means L1, in short you can say that L1 is related with L2, and it implies that L2 is related with L1. So this is symmetric relation. So this is a symmetric relation. Now check for the transitivity. You take another line L3, okay, L3, which is an element of set S. Okay, now third property. Now you see that L1 is parallel to L2, and you have taken another two lines L2 and L3. They are also parallel to each other. Does it imply that the first line and the last line are also parallel? Obviously these two lines L1 and L3 are also parallel. So in short you can say that this is L1 is related with L2, comma L2 is related with L3. So it implies that L1 is related with L3. So this is a transitive relation. This is a transitive relation. So when a relation is reflexive, symmetric and transitive, this type of relation is known as an equivalence relation. So this example is for equivalence relation. Okay, that's all. Thank you friends.